Okay, so welcome back to this next video then, in which we are discussing entropy and the second law of thermodynamics. Okay, so we've seen now then that the second law of thermodynamics says that the entropy of the macro state of the universe always increases. Okay, so remember the universe is this massive three-dimensional space in which we have loads and loads of little particles, okay? And there are a huge number of different microstates that the universe can exist in, okay? So a microstate means you go through every single particle in the universe and you tell me exactly what position it has, okay? So you specify all of the particles' positions. Then you have a certain amount of energy in the universe. You can now distribute this among all of the particles as both potential energy and also as kinetic energy, okay? And there are loads of different ways of distributing the energy among the particles. You can then decide how you're going to bind particles together, all of the electrostatic interactions. You'll have to take all of that into account when you're deciding the position and also the way that you're distributing the energy. All of that will have to be taken into account, and all of those are microstates. Okay, so you know absolutely all of the positions of the particles, you know their kinetic energies, you know the direction in which they're moving, you know the potential energy of all the particles. All of this information you know, and that's a microstate. We're ignoring quantum mechanics here. Okay, this is a classical theory. Okay, so that's a microstate of the universe. Now, of course, we as humans cannot see all of that, okay? What we see is macroscopic states. We see planets and liquids and things like that, okay? So the macroscopic state, or the macro state of the universe, is what we see. Now, the entropy of a macro state, so if you look around the universe that you're seeing right now, that is a macro state. Okay, the entropy of that macrostate means the total number of microstates or that the universe could potentially be in. Remember, there's this massive collection of microstates that the universe could be in. Now, it's in one right at the moment, but the entropy of the macrostate that you see isn't to do with which microstate the universe actually currently is in. What it's to do with is the total number of microstates that the universe could potentially adopt, which would all look to a human as though they were that macrostate. Okay, so they would look like that macrostate to a human. So it's all the microstates that would appear as this same macrostate to a human. So it's the total number of ways that the universe can be arranged on the microscopic scale that would all look like this macrostate to the human. That is what is meant by the entropy of a macrostate. Okay, so the second law of thermodynamics then says that the macrostate of the universe evolves so that in a moment later, the new macrostate of the universe will have a larger entropy. Okay, so the total number of microstates that would all be seen as this new macrostate is greater, basically. That's what the second law of thermodynamics says. It says that you tend to go from a macrostate of the universe that has a low entropy to a new macrostate of the universe which has a higher entropy. Okay, and people often use these terms ordered and disordered to describe this. Okay, so an ordered macrostate basically means that it has a low entropy. Okay, so that's the technical meaning of ordered, low entropy. So a macrostate of the universe will be ordered if it has low entropy, i.e. if there are very few microstates of the universe, potential microstates of the universe, which would actually look like this macrostate. Okay, disordered means that you have very high entropy. So a disordered macrostate of the universe would be one where there are a huge, phenomenally huge number of potential microstates that the universe could exist in that would all appear as that macrostate, basically. Okay, and the second law of thermodynamics says that we're going from macrostates that are low entropy to macrostates that are of a higher entropy. So we're gradually adopting macrostates which are more and more disordered. So obviously if you run this back in time, then what must have gradually been happening since the dawn of time is that entropy must have just been going up and up and up. So we must have started off with a macrostate of the universe that had very low entropy, that had very few microstates, potential microstates that actually would have been seen as that macrostate, and we're gradually going into macrostates now where there are much more microstates of the universe which would actually contribute to that, okay, that would actually be seen as that macrostate. But if you think about it, we're still not that far along. We've still got huge lumps of molecules all grouped together in planets. You know, you'd think that I could create you a mess that would have a far greater number of microstates that would actually be seen as that mess. Okay, so the universe is still quite ordered. It's still got quite a nice macrostate where there are quite few microstates that would actually be seen as that macrostate. Okay, and I mean quite few in the relative sense. Okay, right. So what I now want to talk to you about is the actual definition of entropy, because what we're going to do is we're going to finish this whole video on entropy and the second law of thermodynamics with an actual calculation involving entropy, okay? And we will see basically that the units of entropy are joules per Kelvin, and I can't explain those units without showing you an equation, basically, because so far what I have told you is that entropy of a macrostate is a measure of the number of microstates, the number of potential microstates that the universe could exist in that would all be seen as that macrostate. Okay, but that's just a number. That doesn't have units. So I need to basically modify my definition of entropy slightly. Entropy does represent the number of microstates of the universe that would all be seen as that macrostate, okay? But it's more complicated than that. The actual formula isn't just entropy is equal to number of microstates that would all be seen as that macrostate, okay? So the symbol that does represent the number of microstates that would all be seen as that macrostate is omega. So this means the actual number of microstates that would all be seen as that macrostate. Okay? Entropy is a formula involving this. The strict definition of entropy, then I'll put it on this line and write it nice and big. Entropy of a macrostate is equal to a constant called the Boltzmann constant, which I'll tell you about in a moment, times the natural logarithm of omega. Okay, so the only variable in this equation is omega, so the entropy does only depend on the value of omega. Kb, the Boltzmann constant, is just a constant, but entropy's relation to the number of microstates is not linear, it's logarithmic, okay? So it's kind of like pH, where the pH's relationship to proton concentration is non-linear. Whoops, Boltzmann, not Boltzmann, Boltzmann constant. Okay, and the Boltzmann constant has units, and this is how this equation gets, well, how entropy gets these units of joules per Kelvin. Okay, so omega is just a number. It is the number of microstates that would all be seen as that macrostate. You put it through the logarithm, which is good because it's going to turn this number into a much smaller number, because this is massive, absolutely massive, okay? And when you take a logarithm, that's going to hugely reduce the size of it, because what you're asking, effectively, is what power would I have to raise the exponential number to get omega, okay? So that's what you're actually asking. You're asking, what would I have to put in for x here to get omega? So obviously when you have something in the index, that makes massive things. I mean, if you put in 5, I mean, get your calculator out and put e to the power of 5, you will find a massive number, okay? So with very small x's you can get massive numbers. So this is hugely going to decrease the size of the number that we're dealing with. Now the Boltzmann constant is also a tiny number, so this is also going to help. Okay, so the Boltzmann constant is 1.38 times 10 to the negative 23, and then the units are joules per Kelvin. Okay, so joules are the units of energy, Kelvin is the units of temperature, where we're counting from absolute zero rather than from 0 degrees Celsius. Okay, so this is our formula for entropy of a macrostate. Okay, so entropy isn't quite directly equal to the number of microstates of a system, but you get it from an equation that only involves the number of microstates. So the number that you get for entropy of a macrostate depends absolutely only on the number of microstates that macrostate has which correspond to it. Okay, right, so that's now the rigorous definition of entropy, and this also explains where we get these units from here. Okay, so what we will now do is talk about systems. Okay, so we've been talking about the universe here. What I now want to talk about is a system, and specifically I want to talk about ice melting. Okay, so let's now say we have a container rather than the entire universe. So let's say we have our little science laboratory here. So this is our science lab. Okay, and we have a little container here, and we're going to do an experiment with water. And before I just go on, I want to make sure that you do think that the second law of thermodynamics makes sense. It makes sense that the macrostate of the universe would evolve to a more likely macrostate, just on probability alone. That's all the second law of thermodynamics seems to be. It just makes sense from probability considerations. It makes sense that over time you will adopt a microstate which you will adopt a macrostate which has more microstates corresponding to it, because that's more likely to actually occur if all of the microstates are equally likely. Okay, and remember, we're only having microstates which are actually allowed. Okay, so ones where the amount of energy in the universe actually is the amount of energy in the universe. So you'll have to make sure, that the positioning of the molecules is perfect, because remember, there's all sorts of things to take into account, like gravity, electrostatics, which will all give molecules potential energy, and you're going to have to make sure that the amount of energy you give them is enough to cover the potential energy that their position gives them, basically. So you're going to have to make sure that everything adds up. So the microstates which are actually allowed, that's what we're talking about. So basically all the second law of thermodynamics says is that you will evolve from a macrostate which has relatively few microstates, which actually would be seen as that macrostate, to a macrostate which has more microstates, which would actually be seen as that macrostate. So all it says is basically you'll evolve to a more likely macrostate. All it's saying basically is that the whole universe does the same as when you drop that drop of red dye into a thing of water. You adopt a more likely conformation, basically. That's all it's saying. Okay, so the notation gets a little bit more cumbersome when we're actually talking about systems, which of course we always are, rather than the universe as a whole. So let's say we've got a table here, and we've got a little glass tub of some sort, and we're going to do an experiment within this, and it's going to involve water freezing. But we'll continue this discussion in the next video.